Hello again, and welcome to Advanced Physics for High School students. This is Lesson 39, and it is entitled Electric Potential. We're going to see that there's another word for electric potential that we'll use quite a bit. It is called voltage. And I would suggest to you that voltage is a very important factor in our society, whether you understand it or not. The goal in this course is for you to have some understanding of what it means and how to use it. I would like to introduce you to a short video clip in which there are some linesmen who are working on very high voltage lines. And I think you'll be amazed by what you see.
I don't give two hoots and a holler about flying inside a helicopter. Put me outside. That's where I want to be. On the magic carpet. Back in the late 1800s, there was a gentleman by the name of Michael Faraday. He had a theory that if you enclosed a man in a metal cage and energized that cage at whatever voltage, the man would still live. The voltage would flow around him. I wear a hot suit. It's 75% Nomex for fire retardant and 25% stainless steel thread. And that metal thread means I have a Faraday cage around me. 500,000 volts pass over my body, but I can work without interference from the electricity. As long as the helicopter is isolated from ground, we have the ability to bring ourselves to the same voltage potential as the line, like a bird on a wire. Our pilots are very smooth. It's like they can read our every thought. There's such a hunger for electricity these days. Nobody wants to take lines out of service just to maintain them. I've had many people ask me, do you think what you do is safe? And I say, well, in our operation, everything that we do, every move that we make is thought of and rehearsed before, so it's as safe as crossing the street. It's not a job for a hot dog. There's only three things I've ever been afraid of. Electricity, heights, and women. And I'm married, too.
What you just saw was a film clip of a linesman, say someone working for TVA or for one of TVA's subcontractors, that was doing maintenance on a very high voltage line, maybe 500,000 volts, 500,000 volts, 500 kilovolts. Delivered by a helicopter, the linesman is not electrocuted, and by the time we get to the end of this lesson, perhaps you'll have a better appreciation for how he's able to do that. More importantly, how are you going to be able to solve problems that are posed to you on the AP exam, and what do those problems mean in terms of what's really going on in nature? That's what this lesson is about. Let me say from the beginning that electrical potential sometimes poses problems to early students, people who are just learning about it for the first time. If you are not in the habit of picking up a piece of paper and a pencil and working through examples, then I would encourage you in this lesson that you give it a try and see if that will help you to grasp things a bit better. If you are in the habit of doing that, then I applaud you and I encourage you to keep it up. I hope that'll prove beneficial to you in this particular lesson. So now we want to lay the groundwork. What is electric potential and how do you work with it? And to do that, I want to draw an analogy between a case that you already know. I have two figures here that came from a physics textbook. The one that's on the left is something that you know something about, gravitational potential energy. And the analogy we're going to draw with the electrical potential energy has to do with this gravitational case. In this diagram, I have a basketball that's elevated to a certain height, that's HA. There's a force that's being exerted on it. The force is equal to M times G. The gravitational field can do some work on this object. And the question is, how much work does the gravitational field do? We know that work, if I have a force that is constant, the work is going to be equal to the force times the distance that the object moves. In this case, the force is in the same direction that the object's going to move. It's going to start at point A and it's going to end at point B. The force is equal to the weight of the object, and that force is constant. The work is equal to the force that's exerted on the object times the distance that it moves. And let's call that distance here HA minus HB. Let's call that distance D. The work that the gravitational field does on this object is equal to the force that the gravitational field exerts, which is equal to M times G, times the distance that the object moves. Now what I hope you see in this equation is that what's on the right-hand side looks like the gravitational potential energy formula that we've been using. The amount of gravitational potential energy that the object has with respect to its ending point is equal to the force that's exerted on it times the height, essentially the elevation that the object has with respect to that level. We could call that lower level there the ground, essentially, with respect to which we're measuring our gravitational potential energy. And that work function gives us what the gravitational potential energy is in this particular situation. So now we want to draw an analogy between this situation in the gravitational case with the situation in the electrical case. So let's turn our attention to this right-hand diagram. And the question that we want to ask is, if I have some charge, we're going to call it a positive charge, Q naught, and it moves from a point A to a point B within an electric field, this one happens to be uniform between parallel plate capacitors, then how much work is done on the charge as it moves from point A to point B? Let's suppose that the distance between point A and point B is equal to D, and the force that the charge experiences in the electric field is equal to Q naught, the amount of charge that there is in this test charge, times E, the strength of the electric field between these plates. Well, we would say that the work is equal to the force, the constant force, times the distance that the charge moves. If this is a positive charge, the direction of that force is going to be away from the positive plate that's at the top and towards the negative plate that's at the bottom. So the force and the distance that the charge moves are in the same direction. So what is the work? Well, it's going to be the force, Q naught times E, times the distance, D. And what we're going to see on the right-hand side is something that is a special case for a parallel plate capacitor. It is the change in the electrical potential energy that the charge experiences when it's placed in this electric field. So far we have a direct analogy between the gravitational case and the electrical case. Now it turns out that it's going to be useful for us to talk about the field, the electric field, independent of the charge that's in the field. And when we do this, we're going to be talking about not the electrical potential energy, but rather something that is called the electrical potential. And so there's going to be a difference between potential energy and potential. They're closely related, but they're not the same thing. Here is how we define electrical potential. Electrical potential is defined to be the amount of electrical potential energy that the charge has at a certain point divided by that charge. Symbolically, we use the letter V to represent the electrical potential, and we're going to use several different possible symbols for the potential energy. Sticking with the symbols that we've used so far in this course, let's call it PE with a subscript E for electrical potential energy, and the charge is going to be Q. So we'll write this equation as V is equal to PE divided by Q. And usually we talk about the electrical potential at a certain point. We could talk about the electrical potential that the charge has at point A versus the electrical potential that it has at point B. So we'll put a subscript on these things to try to indicate that. So here, VA, what we mean is the electrical potential that the charge Q, or Q naught in this case, has at point A. It turns out really what we're interested in is not in what the potential is, but what are differences in potential when the charge moves from one point to another. And it is this difference in electrical potential that we call voltage. And so when we say that something has a voltage, say in the case of a D-cell battery of 1.5 volts, what we mean is that there is 1.5 volts of difference in electrical potential between the top of the battery and the bottom of the battery. And a certain amount of charge will gain a certain amount of energy as a result of work being done by the battery pushing the charge around the circuit. In an equation, we'll usually say that the difference in the electrical potential is given by the difference between the potential energies divided by the charge. This will sometimes be referred to as delta V AB. A lot of times the delta is dropped and you'll just see V AB, or sometimes you may just see the letter V. But the idea is the voltage is equal to the difference in the potential energy divided by the charge. One complication that the electric field presents us with is that sometimes I have charges of opposite signs. In other words, I can have positive charges and negative charges, yet I still have to talk about differences in electrical potential. And we'll talk about high potential and low potential. So let me draw a situation here and let's talk our way through it. Here's a pair of charged plates, like a parallel plate capacitor. The left-hand plate is positively charged, the right-hand plate is negatively charged. In between these plates, if I'm not too close to the edges, there is a uniform electric field. We define the direction of the electric field to be the direction that a positive charge would be pushed if it's placed in the field. Now I've got two kinds of charges I could put in this field. I could either put positive charges or I could put negative charges. And those charges are going to be pushed in opposite directions depending on what the sign of the charge is. If I were to put a positive charge in the field, then I would say that the charge has high electrical potential energy if it is close to the left, but it has low electrical potential energy if it's close to the right. The reason that the positive charge has high potential energy at the left is because if I let that charge go and let it accelerate, it's going to gain kinetic energy. It's going to move faster and faster, and it will then turn into kinetic energy. That electrical potential energy will turn into kinetic energy as the charge moves to the right. On the other hand, if the positive charge is close to the negative plate, if I let that charge go, it won't gain as much speed. It won't gain as much kinetic energy before it runs into the negative plate. And so I will say the positive charge has high potential energy close to the positive plate, whereas it has low potential energy close to the negative plate. And we will define the place of high potential, high electrical potential, where the positive charge has high potential energy. So in this situation right here, we would say that the positive plate is the high potential plate and the negative plate is the low potential plate. Well, now what happens with the negative charge? Well, let's put a negative charge in here. Actually, let's put two negative charges in. You can see that the negative charge that's on the right side, the one that's close to the negative plate, is going to be pushed to the left, and it gets pushed a farther distance than the one that's on the left-hand side. So the place where the negative charge has high electrical potential energy is on the low potential side. If I were to take the electron that's on the right-hand side and let it go, you would see that it would gain more kinetic energy as it accelerates across to the left than the electron that's on the left-hand side. if I were to release the electron on the left-hand side, it wouldn't have very far it could go before it slams into the positive plate. However, we still say that the negative plate is the low potential side of this electrical system. The positive plate is a high potential side.